All right. Good morning, everyone. Thank you. A couple of reminders for you at the beginning here. Labs next week. Bring your formula card with tables. If you haven't printed it from C-Tools, do that and bring it along. Bring your clicker and maybe a calculator, because you'll be just doing some probability review and random variable review. Handout will be provided. We've selected some questions for you to try out. So that's the focus of labs next week. You're not going to be on the computers as much. You don't need to do a pre-lab for next week. Homework number 2 is on chapter 7 and 8. There are, again, 9 questions. So your probability review and labs next week will be able to fine-tune maybe some issues for you, but you can try any of the questions out on homework 2 after today's class. We will be wrapping up chapter 8, and that's where the material ends for this homework. Every required homework that's out there also has a set of recommended problems. So you can certainly look at any of those for practice while you're working on the homework, or hold on to them and do them for reviewing for an exam coming up. That works too. Speaking of the exam, a couple weeks yet away, February 17th, but I do need to know if you have a conflict with it. They have been trailing in, more and more students looking at their schedules and seeing that they need some accommodations. So please do check if you haven't. Bless you. And start to make use of the office hours. I had a student last night, about 11:30, emailed me, and they weren't able to get SPSS working through virtual sites. And that was after the homework was due, and can't do a whole lot of help that way. We have computers in the office hour room. You can bring your laptop to office hours. Any of the instructor office hours will be glad to help you. In labs next week, your probability and random variable review may not take the full time. If it doesn't, sit there and use that last 10 minutes and create the one graph you need for homework 2 while you're right there on a computer that has SPSS on it without having to run through virtual sites. In fact, the one graph you need to make for homework 2 is a QQ plot that you learned in your labs this week. All right, do you have questions or comments at all? Questions or comments? We're going to recap discrete versus continuous by doing a couple of clicker questions right at the start. So get your clickers ready. Take a look at our recap first. Random variables. A variable whose value you don't know before you select that person, so therefore it's a random quantity. They can be either modeled discretely or continuously. A discrete random variable has a model where you are able to either list out the actual values of x and their probabilities, and then work out expected values or chances of seeing certain outcomes. Or you might have the probability model, the probability of equaling a certain value, through a formula, like you do for the binomial. In the binomial random variables, we didn't have a table laid out with all the probabilities. We had the formula for how you find those probabilities with that n choose k expression. And you use that to work out then the probability of seeing certain outcomes, probably seeing at least one making a purchase. And then on the continuous side, which we started into last time, we're working with a density curve, a function whose total area underneath it must be 1 for 100%. We worked with uniform densities and started into working with the normal distribution and working with that table. So I've got just 2 review questions. They're short. They will be something that you can probably work out without a calculator, although if you wanted to have a calculator, you could. One will be discrete and one will be continuous. So the first one is a discrete random variable. Happens to be the model for payoff for a lottery game. You either earn nothing, you lose, or you win $5 with those respective probabilities. So the question is to ask here, What's the expected payoff going to be for this particular lottery game? What's the expected payoff? How much will be paid out on average? We introduced expected values on page 40, what was it, 45 and 46. Logically, work it through too. What would you expect the payoff to be? All right, most have given an answer. Expected value, also known as what? The expected value is the mean. The mean or the expected value. We're seeing the prominent answer being a $1, which is correct. Expected payoff, $1. Not which value is going to occur the most. Which value is going to occur the most has the highest probability? 0. 80% of the time, person playing this game would earn nothing, be paid nothing. 20% of the time, they get paid $5. The expected value, big capital E of X, equals the true mean mu. And we found it by taking each value that's possible and not just adding them up. You don't just take 0 plus 5 and cut it in half. That would only be working if they were equally likely outcomes. But here, the 0 gets a much higher weight than the $5 does, giving us a $1 expected payoff. They would expect to pay out about $1 on average for many plays of the game. They'll never pay any one person $1. They'll either pay them 0 or 5. But the expected payout is 1. So how much would you charge to play the game then? At least $1, right? Otherwise, if it's $1 that you charge, then it's a fair game. An even game. If you charge $2, then the house will take in, on average, $1 across many plays of the game. You only have to have a taken amount of a small amount to be able to have the house be the winner, and yet you still would be willing to perhaps play the game. You know, if it costs you $1.05 to play the game, you might be willing to do that. And still the house will come out ahead in the long run. All right, very good. So expected payout, it is the true mean or expected value. It doesn't have to be a value that can even occur for any one outcome. Just like the expected number of people can be 2.5. 2.5 people purchasing online on average out of 10. All right, so there's an expected value. You have to calculate one of those for your homework too. Very simple model. You can see the balancing point is at about $1. And you could work out the standard deviation here too. You have a formula on page 45 for that. Here's another model. Time to deliver a pizza order. Uniform. 20 to 60 minutes. And we ask for a probability that it would actually take longer than 50 minutes to receive the order. We worked on that on page 52 and 53. So this is not a discrete model, this is a continuous model. Time is continuous. Uniform distribution means what? The rectangle. Does a quick visual picture help? Without even drawing the full distribution, you can probably visualize what the answer should be. And it is for longer than 50 minutes. Would you be able to draw the complete picture? Find the height of our density function to work out any given probability, not just an easier one here. All right, let's call that and see what we're doing. Oops, I hope I turn it on. And indeed, most are picking the 25%, which is correct. 50 is right here. That would be 1/4 of that distribution to the right. 50 happens to be what value in this distribution then? It's got a nice name or symbol, Q3, the third quartile. 50 is the 75th percentile, because there's 25% above, 75% below. Good. What is the height going to be here? 1 over what? How long is this? 40. And what would be the label I would give to that y-axis? Density function. That height can be any number. It doesn't have to be between 0 and 1. Density is not probability. The density function is whatever value you need so that the total area under the curve is 1. What if I had a density function that was uniform between 0 and 1/2? Between 0 and 0.5 or 1/2? How tall would the density function need to be there? 0 to 1/2 means the height would have to be 2. 1 over 1/2 or 2. And that's the value of the density function for that curve. Good. All right, now we worked with uniforms. We also started working with the very famous distribution last time and the table to go along with it, the normal distributions or bell curves. We worked with table A1, which is in your notes. Where are we? Page 56 is the table we started working through. Gives us areas to the left for the standard normal distribution. The normal distribution that's centered at 0 with a give or take of 1. And we found areas to the right, areas to the left, areas between two values of z. We even found the 90th percentile at the end. But there aren't too many models out there that are standard normal for variables that we record. Scores on an exam are not going to be centered at 0, give or take 1. Heights are not going to be centered at 0, but we have a way to relate every normal curve that might have a different mean and standard deviation to this one right here by doing the z-score, that standard score. Every normal curve that's out there can be brought back to the standard normal by subtracting the mean and then squishing it or pulling it out to match with a standard deviation of 1 through the z-score. So let's go to a more applicable example where we have a normal model for scores that are given to schools and see how we can work with our table still to find the answers to the questions we want regarding this normal distribution. So what do we have? Schools are rated. They're given scores, an overall score. And if they're in the top 20%, they're called excellent schools. If they're in the bottom 25%, they're labeled as being in danger, maybe in terms of funding or whatever it might be. In the bottom 5%, failing. These scores have what kind of model? Scores points approximately normal with a mean of 75 and a standard deviation of 5. So I can start to picture that model. You could start to draw it. The 75 is your mean. Would that be represented by x bar or mu? That's the mean for the population of all scores, which has a normal model to describe that population. So it would be mu. The Greek letter mu is the population mean. That standard deviation of 5 would not be an S, because it wasn't calculated on just a sample of scores, but it's for the population of all scores, so it would be sigma. Let's draw that quick picture, and that'll help us answer our first question a little more readily. I have scores that are normally distributed. around a mean of 75. Would you be able to put a few other values along the axes? You know that your standard deviation is your yardstick. So 80, 85, maybe 90. And here's a few going out that way. I usually draw the curve and then put tick marks to be 3 of them going out, because that represents just about the whole curve. 99.7% should be within 3 standard deviations. So I know that 70's down here, 80's up here, and so on. So there's my model to describe the scores that schools receive. And my question is, what's the chance that if I selected a school at random, their score would be below 70? Now, can you look up 70 on your yellow card or your formula sheet? Or page 56, where the table's there for your notes. Can you see 70 in there? Is 70 there? Well, these are z-scores. These are the standardized values. What does 70 correspond to, though, on this curve? It is 1 standard deviation below the mean. You have to calculate the z-score first for your observation. Z-scores are always found the same way. Observation minus the mean, divide by the standard deviation. And you get what you makes sense here, a -1, because we're 1 standard deviation below the mean. This particular curve and the area to the left of 70, if I were to translate that curve using the z-score down to the standard normal, the area to the left of 70 is going to be exactly the same as the area to the left of -1. That balloon is preserved, and I move it down, and I squish it up, but that area is still going to be matching up with the area to the left of -1 then. And you can look that one up. On the standardized scale, or z-scale, I have a -1. And can't you look up the area to the left of a -1? Look at page 56 and find the answer for me. Your table is areas to the left, so this is just a straight pulling a value off. -1.00, and what do we get? 1587.1587. The probability that the score would be below 70 is 1587. I can work with any normal distribution. It's related to the standard normal. All you have to do is convert your observation to the z-score, and the area to the right or left of it is the same area to the right or left of your value on this normal distribution. All right. If I had changed this and said, what's the chance of getting a score of 70 or less than or equal to, would my answer change? No. There's no additional area under that curve at a point. In fact, if I had asked, what's the probability a school scored exactly 70 points? You'd have to assign that probability to be 0. You can't assign a probability to any one point because there's an uncountable number of points in there. You have to assign it to areas. So we have to work with areas. If you really wanted the chance of being about 70, you'd take a really small area around that, or plus or minus a little bit. All right, so there's finding an area below, and that was looking up with our chart. The key is I'll be looking for 2 main parts. Show me your z-score, and then use your table and give me the answer. And maybe you have to do a 1 minus of that answer or something, but the main work will be converting to the z-score and then looking up that number and doing things appropriately with it. Our second question has us working with the table in that opposite way, finding a percentile. We're asked here to find the score, the value on the axes that would have a school being called excellent. That means they have to place in the top, what was it, top 20%. So let's think about that picture. I have my normal distribution again, centered at 75. If I'm going to place in the top 20%, what kind of score do I need? Below 75 or above? Above. Top 20%. I need a score, find it, so that the area to the right would be 20%, or 0.20. Which means you really want to find what percentile of this distribution. The top 20%, or the 80th percentile. The area to the left will be 0.8. And the reason why I have to think of it that way is because your table is set up with only areas to the left, not areas to the right. So now I need the 80th percentile of this distribution. Well, the first step is to find the 80th percentile of your standard normal and then unstandardize it. So working with our chart, do you remember how we found our 90th percentile last time? We want the area to the left to be 0.8 here. And so you work in the middle of your chart. Find the closest you can for that area to be 0.8000 and give me the closest value for z. What do you have for the closest value of z? 1 point, what is it? 0.84. Closest value z would be 0.84. Between 0.84 and 0.85. Find the closest. I don't need you to try to interpolate or average between. That means you need to be 0.84 standard deviations above the mean to be the 80th percentile. Anybody not finding the 0.84? If not, ask your neighbor so they can point it out to you. Now, does the school have to score 0.84 points? No. We need to unstandardize it. Set up your z. Figure out how you would unstandardize. When you get your z-score, it's telling you how far away from the mean you need to be in standard deviation units. I need to be 0.84 standard deviations, 0.845s, above the mean. So what score does the school need to have to be in that excellent category? 79.2. Question? No. Take your final answer, make sure it makes sense with your picture that you drew initially. If you get a negative z-score, sometimes it's easy to get the minus and the subtracting worked out wrong. Make sure you're on the right side. Good. Finding percentiles. Would you be able to find Q3 or Q1 for this distribution? Working with your table. Two ways. One problem is you're asking to find a probability, so you're going to need to get z-scores and then work with your chart that way. Other possibility is working with the table and finding a percentile. Common mistake here on this question, students have, but I wanted the 20%, the upper 20%. Don't I have to do a 1 minus of my answer? Sometimes they take 1 minus 0.84 or 1 minus, I don't know, 79.2. They do something that they think they need a 1 minus, but you've already handled that. You just restated the question. The upper 20th percentile is the same as the 80th percentile. So find the 80th and you have your answer, and you don't have to do anything more to it. Okay? So you have a couple examples on your homework too, where you're going to be given a model. It happens to be a normal distribution, and you're going to work out various probabilities or percentiles. A normal model ends up being a model for a lot of random things. And in fact, we're going to see how useful it is as we come back to our left-handed American problem. We tried to work through that on Tuesday, I believe. We said, yuck. And now we have a better way to handle it with a normal model. Page 59? Yep. Our left-handed problem. We had about 10% of our people being left-handed. We were going to take a random sample of a large size, 120. And we wanted to find the probability of seeing 20 or fewer being left-handed in that sample of 120. Now, whenever you're counting how many successes you have out of a fixed sample size, and your success rate's the same for each person, you're in a binomial problem. Binomials are where you have an n and a p, and you're counting the number of successes, where p is that rate of success. So this is truly a binomial distribution for our variable x. The mean would be 12. We'd expect 12 people on average to be left-handed in a sample of 120. The give or take would be about 3.3. The probability could be found in this long formula, finding each one of these with that n choose k formula for the binomial, which would be a lot of work. So there is an easier way to view this. If you think about it, how many values would you have if you were starting to draw the picture for the values of x? X is the number of left-handed in your sample. Just want you to kind of think about this picture, what it would be. You could have nobody be left-handed. You could have exactly 1 or 2 or 3, all the way up to 120. There would be 121 possible values for this discrete variable. Each one of those values would have a probability found with that binomial formula. And if I were to start to draw that model with the heights of the sticks being the probabilities, right around the 12, which is my expected value, I would have a fairly decent stick height. That would be one of the most likely values, because that is what you'd expect on average. And 11 wouldn't be too far off, or 13, and neither would 10, and 14, and so on. And my stick heights would eventually start getting close to 0 down here, and I'm not going to hardly ever see 119 people being left-handed and 120. These would be virtually 0. And what I would have here is a bunch of sticks that if I were to smooth that out, what does it look like? Kind of bell-shaped. If I did smooth it out, it would look more like a bell curve. So what we're going to do is approximate the binomial model with a normal curve instead. Because there's so many values, it's much simpler to have a curve to remember it than to have all the sticks and remember all those probabilities. Here is the result. That gives us an easier way to solve the problem. If you have a binomial, and you have that fixed sample size of n, your probability p, and n turns out to be large, well then you can model that variable approximately as a normal instead. The model for x could be approximately normal, so big capital N for normal. And what goes inside the parentheses when we talk about a normal curve? It's the mean and the standard deviation. That's the symbol or notation we use. So the mean for a binomial was what? The mean was n times p. That's how many you'd expect to see. It was 10% of the 120, or 12 that will go there. And what was the formula for the standard deviation? Binomial standard deviation was np 1 minus p, and then you took the square root, because underneath that square root was the variance. And so that models what I can use. And then I can find areas underneath it to the right or left of any number just by looking up the z-score and working it through much more readily than adding up all those probability sticks. One question we have to address yet is to know when is n large enough. We say n is large. Well, here's the condition that you've got at the bottom there. It's got to be large enough so you will see some successes and some failures in your sample. You would expect to see n times p successes and this many failures. And both of those need to be at least 10. It has to be such that your sample size is big, so you'd see at least 10 yeses and at least 10 nos in your sample. So what's the minimum sample size you could ever have? If you need 10 of each, your minimum would be 20 total, right? And anything more than that might be enough. It depends on your p. It depends on both the sample size and p, because if p is really small, so the thing you're counting is really rare, hardly ever going to happen, you got to start to see a lot more trials before you'll see some of those happen then. There's your little checker condition. One of your homework questions has you apply this. We're going to do it right now. And it does mention you got to show me the check. The condition's met. And that's the condition right there. So let's try it out. Our left-handed American problem. We truly have a binomial model, but our sample size is 120. The mean would be 12, the standard deviation 3.29. To find our probability that we want, can we use this normal approximation? Well, here's the check. That n times p, the expected number of left-handed, is 12. That's at least 10. And that's really the only one I have to check, because if I check the smaller of the two, and it's more than 10, then the other one will be. The other one, of course, would leave 108 expected right-handed people. And they're both large enough so we can use the normal model instead. So what will that normal model be? We just calculated the mean and standard deviation. I can use a normal model centered at 12, give or take about 3.29 for that standard deviation. Not as nice of a standard deviation here, but we can use it. So let's use that normal model to find our answer. How likely is it that we would see 20 or fewer left-handed Americans in our sample? So I'm going to think through and quickly sketch my curve, centered at 12 now. This is the variable number of left-handed in our sample of 120. We'd expect on average 12. My give or take is 3.29, and where is 20 going to fall? Somewhere way over here on the right. And what do I want? The probability of being less. So here's another normal model, just like the one we used for schools' scores. It's normal with a mean of 12 and a standard deviation of 3.29. How are you going to start to find this problem out? You can't take 20 to your table. You have to do what to that 20 first? Standardize it or z-score it? Let's find our z-score. 20 minus what? 20 minus 12 over our standard deviation of 3.29. That's where a calculator is helpful on a homework kind of question where the numbers are not quite as nice. How about if I give you that z-score? 2.43? Now what do? Is my probability 2.43? No, don't ever write a probability down that's more than 1. Look up that z-score in your chart. And again, it's a nice one. You just want the area to the left. So it's just a pulling off of the table. Or some of you got a calculator that has the table internal to it. That works too. So the probability is how much? Pretty likely? What do you get? 9.925? It's quite likely to see 20 or fewer. You'd expect 12. You're much higher than expected, and seeing 20 or fewer happens a lot. 99.25% of the time, you'd see it 20 or fewer in your sample. So if I actually saw in my sample 22 people being left-handed, would you be surprised at that result? Would that result be somewhat unusual? 20 or fewer, all of that's 99%. Higher than 20, less than 1%. So if you saw something that was higher than 20, that might be, that's kind of unusual. That's not typical of what I would see in a sample of 120 people. It might mean that either my population doesn't have a rate of 10% for left-handedness anymore, maybe it's gone higher, or maybe I didn't really take a random sample. Lots of possibilities. That's how we'll be making decisions, is comparing our results and our data to a model that we have to see if it's unusual or not. And that measure of how unusual it is called our p-value, a probability value. All right, our probability is pretty likely here. Do you know what the exact value would be? If you used the exact binomial probabilities, the exact binomial model, your answer would be 9921. That's pretty close. And it certainly was a lot easier to find it by looking up one z-score and finding the area than adding up 21 probabilities from the binomial. Unless, of course, you have a computer that just does it for you. All right, I think I may have mentioned we had an exam question where we meant for you to use the normal approximation because it works really nicely for large samples. And a couple students did the full binomial. They didn't have enough room to write all those probabilities and work them out. And they got their answer, and yeah, we gave them full credit because they did it exactly. But it took them a lot longer to solve that question, which was not intended to be solved that way and take so long. All right. Part B, I'm going to have you try out. It's just another example of doing a z-score and working it through. Chapter 8, we are pretty much wrapping up here. I am going to post those tonight. They'll be my last ones I post in full because the drop ad just passed. And so any student just adding, we had 2 new students adding yesterday. I will always have the notes available in a binder in the office hour room, which is open 40 plus hours every week. And of course, we are capturing these lectures. If you haven't checked that out yet, they're on iTunes U. If you want to review any of our captured lectures, you can do so. And section 8.8, it's a short little half page. We don't need this result until a couple weeks from now, so we'll come back and look at it when we need it. Let's move on to a little chapter 9. This is the good stuff. We're moving into chapter 9, 10, and 12. We have covered in chapters 1, 2, 3, 4, 7, and 8 the tools that we need to now truly do inference. Chapter 9 through 13 is the main inference material, and we're not covering it in that order exactly. There's a couple ways you can go through that material. One would be to take a little piece of different scenarios and then do those pieces again. I like to take the same scenario and cover all parts of it. And so we're going to go through chapter 9, just the first couple sections, and then tie in chapter 10 and 12. If you read through the beginning of chapter 9, it describes that process. The instructor or person that wrote the text kind of gives you that framework. And so we're going to be spending the next week to week and a half learning about a population proportion. Population proportion, which you already have done some work in. Do you remember how we could estimate a population proportion with a sample proportion, p hat? And do you remember the really quick formula for a margin of error for that estimate? What is it, 1 over square root of n? We're going to see again before the end of next week where that 1 over square root of n came from and why that is the 95% margin of error for a proportion. So here's the idea. Chapter 9, the first section talks and sets this up. There are parameters out there. There are statistics that we use to estimate those parameters. That's inference, trying to learn about your population and various aspects of your population by taking a sample and calculating the stuff on your sample and saying, well, I think then the population rate is 60% because that's what my sample said. You had, even on homework 1, the distinction between a population versus a sample. The population is the entire group you want to learn about. You can think of it as a big basket of balls with a ball in it for each person. It's a very large basket. A sample would be the selection of a few balls from that basket, a few people from your population. The parameter goes with population. A parameter is what you calculate on the population. You want to know about the true proportion who would vote for that candidate? That's your parameter. We call that P. How are you going to learn about it? Take your sample. Take your, what kind of sample do we want? A random sample, representative of our larger population. And on that sample, calculate the same thing, the proportion who would vote for the candidate. And you've got an estimate. You've got a statistic. Anything that you calculate on a sample is called a statistic. You might have the sample proportion. That was what, P hat. You might have the sample mean. We call that X bar. Those are statistics because they're calculated on the sample. We're trying to use the sample to make judgments or decisions about the population. Okay, our sample of people saying they're going to vote for that candidate is 60%. Can we statistically say we have a majority? Because I know if I took another sample, the same size, I might get a different answer out. It's not going to always be the same. So that's where we're going. A quick question to kind of review that. That's our last clicker question for today. I'm going to give you a scenario, and there's a number in it. It's highlighted. Is that number a parameter, or is it a statistic? All right. Parameter goes with what? Population. Statistic goes with sample. So we have a polling organization that surveyed 100 adults. 72% were in favor of tougher penalties for drunk driving. Parameter or statistic. Most of you are doing just fine. All right, we're going to call it. Ready? Last call. And here are what your answers are. Most of you said, indeed, a statistic. It was a survey. Those 100 adults are not all adults in Ann Arbor, but only 100 of them. It is a statistic. Can you tell me what the symbol would be? Would I call that P or P hat? Which one? P with a hat. Hat means estimate. We put hats over things when we're estimating those things. Would you be able to work out the margin of error for me? What would the margin of error be that I would associate with that estimate? 1 over square root of 100. It's all based on the sample size. So 10%. So I would actually estimate it not to just be 72%, but I might go from 62 to 82% and say, I'm 95% confident. The true proportion of all adults who are in favor of the tougher penalties, somewhere between 62 and 82%. Would you be satisfied as saying you have a majority? 62 to 82%. All completely above half. Now, what if I took another sample of 100 adults from the same population? Am I going to get 72% every time saying yes? They're in favor of? That's going to vary. That statistic can be thought of as a random variable. That statistic, p hat, is going to vary from one sample to the next. So it has a distribution, a model, to describe how it varies. And that distribution is called a sampling distribution because you get it by taking samples over and over. That's a tough concept, but we're going to go through it. We are going to go through all 5 scenarios that are described in section 9.2. 9.2 is a nice little intro to read. For exam 1, we're only going to get through the first scenario, proportion. For exam 2, we will have covered all 5. We call them the big 5. We're going to show you how to learn about population proportions, or the difference between two proportions. How do males versus females differ in their rates of favoring tougher penalties? And then we will turn to means. And we will have single means, we will have 2 means, because we often know we want to have control in our experiments with a placebo, or with maybe at least a standard drug being given against a new drug. So we will be going through these 5, but we're going to focus on a proportion first. 9.3 defines generically this thing called a sampling distribution. Everything that you calculate on a sample is called what again? Is it the parameter or the statistic? Statistic. A statistic is going to vary from one sample to the next. You don't get the same answer when you take another sample and calculate that same proportion for that new sample. It varies. So it is a random variable. It'll have some kind of probability distribution, and we've been studying probability distributions in Chapter 8. The name of that probability distribution is called a sampling distribution. So what is a sampling distribution for a statistic? It's just showing you all the values you could get for that statistic, and again, how often they would occur. So you have an idea, a frame of reference of what you'd expect. And then you can see if your result is consistent with that or unusual under that. So the first statistic we're going to work with is a sample proportion, p hat. Let's, oops, going backwards. What's going on there? There, oh, I have my pictures of the day next. Let's do that first, shall we? I don't even remember what pictures they are. Oh, there they are. How many of you have heard of Webkins? Anybody? Sisters, smaller sisters that have those? Yep. The first Webkins my daughter received a number of years ago was a hippo, a blue hippo called Hip. And that blue hippo went everywhere and still does. In the backpack and not always pulled out anymore, but it does. And that blue hippo had to go visit in Florida when we went to see grandmas and grandpas, the Hippo Gorge. So she brought it with and carried it around the whole day. So there's Hip the hippo, and that's an actual hippo right there. Okay. Hippo Gorge. Do you still have your favorites? Did you have a little animal or blanket or something? All right. And from that, we go back to sampling distributions. All right, let's see if we can identify the different parts. Can you distinguish between the population and the sample? Can you distinguish between the parameter and the statistic? Here's a poll. It was conducted by this Center for Workforce Development. They took a probability sample of 1,000 workers. It was actually not a random sample, it was a stratified sampling technique, but it involved randomness. And out of those 1,000, 460 or 46% said they typically work more than 40 hours per week. So they polled full-time workers and asked them, how many hours per week do you usually work? Is it more than 40 hours or not? So what's the population versus the sample? Who are we trying to learn about here? Population, you usually use the word all. All what? All would be full-time workers, because we're talking about whether they work more than 40 hours per week. All full-time workers. This was focused in the United States and not worldwide. And then in contrasting that, what is actually the sample? Not all full-time workers, but the 1,000 that we surveyed. All right. Parameter versus statistic. Parameter is the thing that we would like to know and calculate, if we could, on the entire population. What are we trying to learn about here? The proportion who work more than 40 hours per week. I would like to learn the proportion of all full-time workers that work more than 40 hours per week, and that would be my parameter. I would represent that parameter with P. We have that notation P representing what? It's a proportion, but what kind of proportion? The population proportion. Whenever you write the word P and have to define it, start out with the population proportion of all workers that what? The characteristic is that they work more than 40 hours per week, abbreviating a little bit. Or P is the proportion of all workers. It's the true proportion, the true rate. Contrast that with the statistic, which would not be the proportion for all workers, but the proportion for my sample of 1,000 workers. And the symbol for that would not be P, but P hat. P hat will be the sample proportion. The proportion in my sample that say, yes, they work more than 40 hours per week. Which of those values do we know, P or P hat? We know P hat. P hat is what? That 46%. P hat for this one sample is known. We have that P hat for our one sample is 0.46. Once you observe the sample, you have your answer to the statistic. Do we know P? No. If we knew P, we wouldn't need to take a sample to try to estimate P. P, however, is a fixed number. It's just unknown. The true proportion P, the parameter, is always a fixed value. We don't know it because the population is too large to be able to actually get that value, so we go to a sample and calculate an estimate of it. P hat here is 0.46. But what if you did this survey again? 1,000 workers again. Are you going to get 0.46 every time? No. So which one varies, P or P hat? P hat. The statistic is the thing that varies. The parameter is fixed, but unknown. So this value P is a fixed, unknown quantity. The value of P hat will vary from one sample to the next. And that's the discussion that we've got in the bottom of that page. Let's answer those couple little questions. Can anyone tell me how close is my 46% to the truth? That's the first question. Can you say how close the observed value of 0.46 is to the true proportion? How close am I? Was it a good estimate? I have no idea. I don't know how close 46% is to the truth because I don't know the truth. So how can I say how far away it is? We can't. No, P is unknown. If we were to take another random sample of 1,000, are we going to get the same value for P hat every time? We've already answered that. That is no, not necessarily. We might get a 46% again somewhere, but it's not going to be the same each time. So what are the values that you could get for P hat? Could it be anything between 0 and 1? Or would you hope that it would be not varying that much? And I hope that would tend to vary around what? I'm hoping that these values for my sample rate would tend to be really close to the true rate. I hope that if they vary around it and not very far away from it. I want to know what the distribution for values of P hat would look like. And we do have a result. Guess what kind of distribution it's going to have? A bell curve. We studied the normal distribution because a lot of things end up having a normal distribution. There's a couple of pictures for visualizing it on the next page. We're just going to put a few X's or sketches in here and then give you the result and maybe apply it to get an idea of that bias that we talked about earlier. All right, R1 P hat is 46%, 0.46. We got a value right about here. Putting my first P hat value on the axes. Take another random sample. Same size, from the same population, in the same random way, and you're going to get another P hat. Suppose in that case, that P hat was 420 out of 1,000, or 0.42. So now I've got a 0.42. And I want you to imagine doing this over and over and over again. Now, this is not what statisticians do. They don't sit in their office and keep taking samples over and over and over again from the same population. We have to imagine what would happen if you did so we know the result. And that result at the end is what we get to use when we do it the one time we do it and make a decision about it. If you were to do it over and over again, you're going to get lots of values. And they are going to vary and start to accumulate up. And guess what kind of model you're going to start to see here? I already gave it away. These values will vary. You'll occasionally get some that are a little extreme, but if you were to smooth it out, you get a normal distribution. And this is over values of 1,000 for your sample size. It's not going to be all the way down to 0 and all the way up to 1, as long as you took a decently large sample size. If you only took a sample that's really small, then there's only a couple of values you could get, and yes, out of 2 people you can get nobody or 1 or 2 out of 2, but with 1,000 people, you're going to have some variation, but just not too much. What if we doubled our sample size? All right, let's make a couple observations here first. What do we observe? The values do vary. And they are approximately bell-shaped or normal. Approximately bell-shaped distribution. And we're going to see that again. If we were to change the scenario and take a sample size of 2,000 instead of 1,000, but there will be some aspect that will change. What do you think? What if our sample size was even larger, double it? What's going to happen? We might still get a 46% the first time. That would be, though, from, say, 900 out of 2,000. Maybe we get 46. Maybe we do it again, get another p-hat, 0.45, and keep going for samples of 2,000 over and over. And again, I will get some variability, but that amount of variation will be less. Smaller spread. Again, the values do vary. They will not all be the same. They will be approximately bell-shaped. Less spread out. Does it make sense that if you took a larger sample size, your answer should be more accurate in some sense? We know that if you took a larger sample size, your margin of error would go down. And that's reflected by the fact that my standard deviation here would be less. I may be off from whatever the truth is, but the amount that I would be off would be expected to be less. It's reflected in a smaller standard deviation. In both cases, we're getting a bell-shaped model. So let's tell you what that model would actually look like so we could use that result to answer a good question. Didn't we just use the normal model a few minutes ago to answer the left-handed American problem? Right? Didn't we just establish that if you were counting the number of successes in a large sample, instead of using a binomial, you could do it as a normal model instead? So that's this first result as a recall. We have already seen, really, the first sampling distribution for x, the number of successes in your sample. There's the model for the count. But now I'm not just counting how many said yes, I'm converting that to the proportion that say yes. How do you do that? Count over the total sample size. So what's going to happen to this model? I'm basically dividing by n. So I have a proportion instead of a count. N times p is what you'd expect for the count. Divide that by n and you get p. On the standard deviation side, it's a little trickier. You have to actually put the n on the bottom for the variance, which actually gets squared. So there's going to be a square n underneath that square root, which will cancel out with one of these guys up here. So here's the result. Sampling distribution of p hat, bottom of your page. If the sample size is large enough, again that n times p, there's at least 10 rule, then not only is the count going to be approximately normal, but the corresponding proportion p hat would also have this normal model. Just update the mean to be p instead of the n times p. And the standard deviation now looks like this, with that n on the bottom. What does that mean? The values of p hat, the values that you could get for your sample proportion, when you go and take a survey and ask them the question, they will be expected to vary around the truth. On average, you would expect to get the right answer. You won't get the right answer every time you do it, but at least on average, you're right on. That's called unbiased. It's a technique for estimating a true parameter that's unbiased. And what do we know about the standard deviation? It would be this expression, p1 minus p over n. That's the formula for that standard deviation. What's nice about that formula compared to the other one? Where is the n? On the bottom. So what happens to that standard deviation if your sample size gets bigger and bigger and bigger? Standard deviation gets smaller and smaller and smaller, which means my normal curve goes even taller and right around the truth, which means my answers to my survey results should start to be more accurate towards that truth. All right, so let's use this model to do one more example. We kind of talked about this in chapter 4, I think it was. Do Americans really vote when they say they do? Right? We talked about if we had called up people and asked them, do you plan on voting in the election? And if we were to compare those results to what actually happened, they don't always agree. Here's a telephone poll taken a couple days after an election. 800 adults were asked if they had voted, and 56% said, yes, I voted in that election. The results from the actual election, though, showed 39% of eligible adults voted. But of the 800 adults that were eligible to vote, 56% of them said they did. So I know that if I take a sample, I will not always get the right answer every time. But the right answer should be about 39%. I got 56%. So what I want to work out is kind of get a frame of reference here. What would I expect to see? And is my 56% just a little bit big or really big compared to that expectation? So in this problem, you're given 800. That is what? That's my sample size. Was it pretty large? Probably large enough to use my normal results, I hope. 56%. What is that number? Is that the statistic or the parameter? Is that p hat or p? P hat. That's the sample proportion that I got for my one sample of 800. Now, I happen to know the truth here. This is after the election is over, so I have the actual true value p. Suppose 39% is the correct proportion. Let's assume our 800 adults are a random sample. Let's first describe how we expect a sample proportion to vary in this kind of problem. The sampling distribution of p hat. Well, that's the box on the previous page that we just wrote out. What is that model going to be? If our sample size is large enough, we get approximately normal. The mean is supposed to be p, so it should be centered around what? 39%, 0.39. And then what is that new standard deviation formula? Square root of p, 1 minus p over the n. This is the standard deviation for a rate, for a proportion, compared to the one we used a little while ago for a count. So I have to calculate that. What's it going to be? 0.39, 1 minus that, over 800. And I'll give you that answer, but I do want you to try getting that on your own sometime, because when you get really tiny numbers like this, I mean, proportions are between 0 and 1, standard deviations are even smaller, you'll get scientific notation sometimes coming out in your calculator. So you want to be comfortable with working with that. You should get about 0.17 as your standard deviation. Would you be able to start to draw that picture for me? Here's what you could get for values of p hat. Centered at 39, and I bet you could do a couple tick marks if you needed to, right? 0.39 plus 0.017, so 40.7%. And on the other end, can you already start to see where your 56% is going to sit? Way out there somewhere. So you have a normal model that describes the values you should get for p hat. And part B asks you to figure out how likely would it be to get 56% or even higher if the true rate is really 39%. How likely would it be to observe what we got, or something even more extreme than that? So let's use that sketch, that idea. If I need to find the probability of seeing 56% or higher, how do I do that? It's a normal model, but it's not normal 0, 1. So what's the first step I need to do? Get a z-score. The z-score is always found the same way. Take your observation, 56% is what we got, subtract the mean, and divide by the appropriate yardstick, the standard deviation. And guess what you get? Anybody calculate it yet? Standard deviation on the bottom there gives me that I'm 10 standard deviations away from the mean. Now, many students, when they get a z-score of 10, they think they calculated it wrong. because, z should be between plus and minus 3, mostly. But this is telling you something. You can get a z-score of anything. Remember one homework question a while back in a term, the z-score turned out to be like 17 point something, and everyone thought they got it wrong. They were coming in and asking. No, it's though telling you that what you got doesn't match with that model you had at all. What's the answer to our probability question here? How likely is it to get 56% or higher without even looking it up, because you don't really need to look it up? You're off the chart. Your probability is practically 0. The chance of getting on a standardized scale 10 or more, hardly nothing over there. 0.000000001 somewhere. Virtually impossible to see what we got in our sample if the true proportion is really 39%. So what does that mean? What does that mean? Does our poll result of 56%, is it reflecting a sample that just by chance voted with higher frequency, said they voted with higher frequency, or is there something else going on here? If we said it was just due to chance, well, that's really unlikely. What's the possibility here? What kind of bias is probably playing a role? Response bias. People did not want to answer this question honestly. They didn't want to sound unpatriotic. So they said, yes, they had voted when they really had not. We have now an idea of how much that bias could be. We could actually do studies like this to estimate the effect of the bias, so when you do get answers from future polls before the election, you would know how to account for that bias. So does it seem that the poll is showing just that chance variability? Our answer to this would be no. Rather, it appears that the respondents weren't all telling the truth. Otherwise known as having the problem here of response bias. They all responded. I had 800 observations, very small non-response rate. So it wasn't non-response. It wasn't that I didn't select a random sample. I did. It's response bias, the culprit here. All right, that is it. Have a great weekend. Come up if you still have a question.